Neon is one of the most recognizable elements in the periodic table, not just for its scientific properties, but also for its cultural impact, particularly in the world of lighting and advertising. It has the symbol Ne and atomic number 10, placing it in the noble gases group alongside helium, argon, krypton, xenon, and radon. As a noble gas, neon is colorless, odorless, and extremely unreactive under most conditions, thanks to its full outer shell of electrons, which makes it chemically stable and rarely forms compounds. Discovered in 1898 by British chemists Sir William Ramsay and Morris Travers, neon was identified during experiments involving the liquefaction of air. By cooling air until it became a liquid and then slowly warming it, the two scientists were able to isolate different gases that evaporated at distinct temperatures. After removing oxygen, nitrogen, and argon, they identified a new gas that emitted a brilliant red glow when electrified. This was neon. The name neon comes from the Greek word neos, meaning new. Interestingly, Ramsay and Travers discovered krypton and xenon within a few weeks of neon, but it was neon that quickly captivated the public due to its luminous properties. In its natural state, neon is quite rare on Earth. It makes up only about 0.0018% of the Earth's atmosphere by volume, and it's even scarcer in the Earth's crust. However, it is far more abundant in the universe, particularly in stars, where it is created through the fusion of helium and other light elements. Neon's cosmic abundance places it as the fifth most common element in the universe, following hydrogen, helium, oxygen, and carbon. Despite this abundance in space, neon is not commonly found in compounds or minerals on Earth, which is why it has to be extracted from the atmosphere through a process called fractional distillation of liquefied air. Neon has several unique physical and chemical properties. It is lighter than air, and like all noble gases, it is monatomic, meaning its atoms do not bond together to form molecules. It has a boiling point of -246 degrees Celsius and a melting point of -248.6 degrees Celsius, making it useful in extremely cold environments. In fact, liquid neon has over 40 times the refrigerating capacity of liquid helium and about 3 times that of liquid hydrogen, making it an effective cryogenic refrigerant, though its cost limits widespread use in this capacity. Most people associate neon with its use in lighting, particularly the iconic neon signs that lit up cities throughout the 20th century. When a high voltage is applied to a sealed glass tube filled with neon gas at low pressure, the gas emits a bright reddish-orange glow. This phenomenon is due to the excitation of neon atoms. When energized, electrons in neon atoms jump to higher energy levels and release light when they return to their original states. The characteristic color of neon light is a direct result of this process. Other colors seen in neon signs are usually produced by different gases or fluorescent coatings inside the tubes, not by neon itself. The first commercial neon sign was introduced by Georges Claude, a French engineer and inventor in 1910. By 1923, neon signs had reached the United States, where they quickly became a symbol of modern advertising. Businesses used them to attract attention, and soon neon lighting was an essential part of urban nightlife and visual culture. Despite the decline in their use due to the advent of LED technology, authentic neon signs remain popular in certain design niches and are appreciated for their craftsmanship and nostalgic appeal. In addition to its visual applications, neon has some important scientific uses. It is employed in vacuum tubes, high-voltage indicators, wave meter tubes, and television tubes. Because of its inertness and low reactivity, it is often used as a protective atmosphere in certain types of welding and in the manufacture of semiconductors. Neon is also used in gas lasers. The helium neon laser, for instance, is one of the most common types of gas lasers and is frequently used in barcode scanners, alignment tools, and laboratory demonstrations. These lasers produce a coherent beam of red light and are valued for their stability and precision. One of neon's less known but scientifically intriguing properties is its isotope composition. Naturally occurring neon is a mix of 3 stable isotopes: neon 20, neon 21, and neon 22. Neon 20 is by far the most abundant, making up about 90.5% of natural neon, followed by neon 22 at 9.2% and neon 21 at 0.3%. These isotopes are used in a variety of research contexts, including the study of solar wind and cosmic rays, as well as in geochronology to help date certain types of rocks and geological processes. Neon also plays a role in the field of astrophysics and planetary science. Its presence in the atmospheres of planets and in the interstellar medium can provide clues about the processes of stellar evolution and the formation of planetary systems. For example, studies of neon in the sun's corona help scientists better understand solar activity and the behavior of plasma in high-energy environments. Although neon is not toxic and does not pose a chemical hazard due to its inertness, it can be an asphyxiant in high concentrations because it displaces oxygen. That said, such situations are extremely rare outside of industrial or laboratory settings. Safety considerations are generally minimal compared to other industrial gases. From a broader perspective, neon embodies the intersection of science, industry, and art. Its discovery marked a turning point in our understanding of atmospheric chemistry. Its application revolutionized visual advertising, and its ongoing use continues to support both technological and scientific advancement. Whether illuminating a diner sign or enabling precision measurement in a physics lab, neon stands as a testament to how a seemingly obscure gas can have far-reaching impacts across multiple fields. As we continue to explore new materials and technologies, neon's place in the periodic table and in human culture remains secure, glowing as brightly in the scientific imagination as it does in the real world.